Scaling and similitude are quite important when talking about turbo machines. This is because when designing for a turbo machine, we are usually able to do an experiment on a small scale model of the turbo machine, and then we move on and carry out we transfer the results that we get from our small scale machine onto the large scale machine. So this is the next topic that we are looking at, and under scaling and turbo machines and similitude, we shall first of all look at the dimension analysis and performance. Then we shall apply this to low-speed machines, and then also apply this to high-speed machines, and then consider the concept of specific speed. So formally, we can say that similitude and dimension analysis is concerned with using models to predict the performance of the actual machines and to investigate the performance of a given machine under different operating conditions. So when we apply dimension analysis on turbo machines, we do this for the following reasons. First of all, when talking about turbo machines, we have a large number of variables which are involved, and dimension analysis is able to reduce the variables to a manageable number of dimensionless groups. Usually the groups are like three, 4, even 5 groups, but these are as opposed to the parameters involved, which could be up to 8 or 9. The second use is that dimension analysis can be used to predict the performance of a large-scale machine of a prototype from the tests that are conducted on a small-scale model. So for this, we carry out the test on the small-scale model, then we are able to actually implement this in the large-scale machine. The third is that dimension analysis assists us in the determination of the most suitable type of machine for a given application. And this is because when talking, for example, about specific speeds, we know that various types of machine have different specific speeds, and based on these specific speeds, we are able to select the appropriate type of machine for the appropriate type of application. So there are 7 fundamental dimensions which we usually use in physics for describing a physical phenomenon. The first is mass. The second is the length dimension, L. The third is the time dimension, which is T. The fourth is the charge dimension, Q. And the fifth is the temperature dimension, which is theta. Usually for mechanical systems, we are only concerned with mass, length, and time scale. But in case we have heat transfer, then we are also able to use the temperature to be able to analyze our physical phenomenon. We can also get the dimensions of other units that we use. For example, when we're talking about the units of pressure, we know that pressure is force over area. The dimensions of area is L squared, and the dimensions of force is mL over T squared. So if you are looking for the dimension of pressure, we take mL T squared and divide it by the dimension of area, and so we'll get that for pressure, the dimension is m over L T squared. So when trying to analyze the operations of our dimensions, then we usually rely on the principle of dimensional homogeneity. This is also called Fourier's principle of dimensional homogeneity. And this just states for us that for an equation to be valid, the dimensions on the left-hand side of the equation should be similar to the dimensions on the right-hand side of the equation. We usually use 2 methods in trying to analyze the dimensions of a physical phenomenon. The first is Buckingham's pi method, and the second is what is called the Ingersoll method, or sometimes also called Rayleigh's method. So when looking at fluid mechanics, We typically deal with a few dimensions. The first is the volumetric flow rate, which we can refer to as Q. And the volumetric flow rate basically refers to how much volume of fluid flows per unit time. The second dimension, which we deal frequently with, is the energy per unit weight. This has the dimension of length, and we usually call it to be a head. Another dimension that we deal with frequently is the dimension of the turbo machine, and this is usually the characteristic dimension, usually the size of the rotor. So typically it will be the diameter of the turbo machine. Another parameter that we deal with is the power that is either produced or consumed by the turbo machine. Very important is the fluid characteristics, the first one of which is the density of the fluid. And the other important fluid characteristics is the viscosity of the fluid. An important machine parameter is the rotational speed of the machine. We note that the dimension of the machine is a length characteristic, and the energy per unit weight is also a length. So to avoid confusion, we usually use energy per unit mass instead, which is GH, and this will now give us a different dimension. So for a typical flow within a machine, we can say that the relationship, the functional relationship relates the discharge, GH, the diameter D, the power P, the density rho, the viscosity mu, and the rotational speed omega. So we can say that functional relationship is equals to 0. And then for each of these, we can consider the dimensions. So the discharge is length cubed over time, the mass, the volume flow rate. For GH, the dimensions are L squared over T. For D, the dimensions are L, length dimension. For power, the dimension is ML squared over T squared. For the density, the dimension is mass per unit, per cubic length per unit volume. For the viscosity, the dimension is mass over LT. And for the rotational speed, the dimensions is 1 over T. So when carrying out a dimensional analysis, we need to consider each of these. And in our case, we know that the variables that we are talking about are 1, 2, 3, 4, 5, 6, 7. So n is equals to 7 from Buckingham's pi theorem. And then m, which are the fundamental dimensions, is length, time, and mass. There are no other dimensions involved. So m is equals to 3. So our n minus m, with the number of dimensionless groups, is usually equals to n minus m, which is 7 minus 3. So that will give us 4 dimensionless groups that we should expect when we carry out Buckingham's theorem on this analysis. So if we go ahead and carry out the dimensional analysis, we can select our repeating variables. And we can take them to be rho, which is a fluid property. We can take omega, which is characteristics of the flow of within the machine. And we can take D, which is the characteristics of the machine. So this will be repeating variables, so that for pi1, we'll have the repeating variables rho, omega, and d. And we can say this is power A, power B, and power C. And then we take one of the other variables, Q. For pi2, we'll again take the repeating variables rho, omega, d. And this is power D, E, F. Then we'll take one of the other variables, GH. The third pi term will again take rho, omega, and d, and then this will be f, g, h, I. And we shall take one of the other variables, p. Then for pi 4, we'll take again the repeating variables rho, omega, d. And so here will be j, k, and l, and we'll take one of the other variables, m. So for us to be able to carry out an analysis, we'll say that the dimensions of the pi term will be equivalent. On the left hand side, we'll have the dimensions of rho, which is m l by minus 3 power a. The dimensions, we are looking at this first pi term here. So the dimensions of omega, we have said, will be t minus 1, and this is power b. Then the dimensions of d is just a length dimension, so this is l power c. Then the dimensions of q, the discharge, will be l cubed per unit time, t minus 1. And this should be equivalent to m null, l null, t null. And then we look at our analysis here. We can look for each of these. So for m, the dimensions that we have for m is a there. Then there's no other value for a. So we'll say that a is equals to 0, because it's just this a, and we have 0 on the right hand side. For t, on the left hand side, we have minus 1b, and we have minus 1. So for t, we can say that minus 1 minus b is equals to 0, from which we can say that b is equals to minus 1. For l, when you look at the left hand side, we have minus 3a, and then we have c, and then we have 3. So for l, we can say that 3 minus 3a plus c is equals to 0. So from which we can see that a is equals to 0, so that is equals to 0, and c is equals to minus 3. So from this, we are able to get our first pi term. So pi 1 will be equals to q over omega d power 3. So this is what is usually called the flow coefficient. So you can also refer to it as pi q. So this is our first pi term.